Okay, so after knowing isotropic and knowing these materials, alright, and knowing the behaviors of the material, let's talk about the matrix, alright, that deals with all of them all together. In this system, or in this video, we'll talk about stress strain, which is this one, alright, for isotropic material. Okay, the reason why we want to look into the matrix form, alright, in terms of a stress strain, is that we are actually keen to know what is the amount of strain, alright, how under certain load, alright, what is the change in length of the material such that it is able to sustain. In other words, you know that the limitation of the strain for your composite is 0.5 millimeter. If it exceeds 0.5 millimeter, the composite material will break. Alright, will break. So therefore, once you set up the matrix and then you calculate for your strain, you have to ensure that your strain values is going to be lower than this thing. Alright, this is just my assumption of how this is being used, but at least you get to see that there is an importance in the matrix and why do we want to have the stress strain matrix for. Yeah, okay, so therefore and therefore in order to do this, we have to first understand a stress tensor. Alright, so a stress tensor, actually I would assume that this is actually a principal stress. Or if you happen that you forgot or you don't know anything, you can come to this playlist. Alright, so you come to this channel and search. You can click created playlist. Alright, so once you click it, and you will find SEM3 Mechanics 4N, and if you have to click this SEM3 Mechanics 4N, you'll come here. Alright, and you can just search for your whatever thing that you want. So for example, if I want to search for principal stress, then you can come here. This is the principle of virtual displays. Yeah, so if you search for principal stress, this one will come out. Alright, and you can just read it up yourself. And the other one is to prove that a stress tensor is a symmetry, which is this one. Okay, and I'll not go into details because this is something that you have known. Alright, but in case whoever that may need it. So therefore, the stress tensor is actually a symmetry, okay, which is only this portion like this. So they are actually the same in both sides. Okay, and this is the trace of your stress tensor. Alright, where we say that this is the principal stress, sigma 1, sigma 2, and sigma 3. Or these are the normal stresses perpendicular to the plane. As you can see, this is the normal stresses. While the shear stresses, alright, gamma, these are the tau. Okay, these are the tau. So 1, 2. Yeah. Yeah, correct, like this. So therefore, this part over here will be the same as this portion. So this is tau 1, 2 also, tau 2, 3, and tau 3, 1. The same thing as this portion. Okay, this is why it's saying symmetry. This is only for the stress state. So it's talking about the state where your material is under a certain stress. Alright, but however, we are keen to look at the strain because there is a requirement of the strain. How long can the strain be allowed before it cracks or whatever. So therefore, we're going to translate this one in terms of a certain strains, as you can see. So these are all your strains, and your shear strains are all your gammas all over here. So it's the same thing I'll write as gamma sigma, yeah, like that. And then over here I'll write this stuff. Alright, these are all your shear components. So this portion over here is your shear components, while this middle one is your so-called normal components. The normal means that it is normal to the plane. Okay, while the shear components are the one that's trying to deform the cube. Okay, this will talk about the devolteric and principal stresses. So this is why I highly recommend you just search for principal stress, and then over here they will define hydrostatic and devolteric. So this is a very good video for talking about both of them, hydrostatic and devolteric and principal stresses. So if in the future you may forget whatever, you can actually hit there to check it out. And these equations is the equations that we have shown you earlier in the previous video talking about isotropic material. Alright, so the isotropic material has this certain equation, okay, and if you translate into a matrix, okay, you have something like this. I'll not go into details on how do you translate that, but I'll just do this example to show you how is it done. Okay, if you find it very boring, you can skip a few minutes later. Alright, so strain 1 over here is equals to 1 over E times stress times 1, right? So 1 over E times stress 1 is equals to this portion. Alright, but you know that 1 over E we're going to multiply inside. Alright, so 1 over E times minus V, you'll have minus V over E times sigma square. Alright, which is this one. You get what I mean? Okay, so in order to illustrate properly, alright, so this is the equation that I've shown you. Alright, I'm multiplying this into here, I'm multiplying into all this thing. As you can see, this 1 over E is here and over here. And I'll expand this 1 over E times the Poisson ratio. I'll have this form and this one. Okay, so I'll label them in different colors, so at least you get to see them in a more easier way. Okay, you give me a while. Okay, so therefore this 1 over E times sigma 1 is actually 1 over E times sigma 1, which is this one. Okay, then this minus 1 over E times Poisson ratio sigma 2 is minus 1 over E times V is actually minus V over E, and then multiply by sigma 2, which is this one. Okay, and then minus V over E times sigma 3, which is this one. Okay, so therefore this first row, alright, will represent this one. Alright, subsequently the second row, as you can see, this one will be represented over here, third row will be represented over here. Alright, while the rest of the gamma will be represented over here. I'll not go into details, but at least it's pretty clear for you right now. Alright, and therefore this whole stiffness matrix, alright, this whole thing is what we call the compliance. Alright, this whole thing is called the compliance. Alright, and this is the compliance relates, alright, multiply stress in order to get strain. If this thing over here is strain, then there is another term, I call this the modulus, I think, I forgot what's the name. But anyway, okay, it's called the stiffness matrix. Alright, this is the strain. If you have the strain over here, this is called the stiffness matrix. Okay, if you have the one that I've shown you, this one is the stress, this is the strain, you're actually talking about the compliance. Alright, so this whole thing is a compliance. Previously in that section, alright, this is the stiffness matrix. Alright, this thing is the strain, right? Now over here, this thing is the stress. There's a difference in there. Okay, if you don't understand anything, you can just click compliance, or find the compliance, and you'll get into this video. You can watch the meaning there. Alright, then and moreover, these definitions you can also be understood from this video. Okay, these are all just the tensor indications, that's all, initial notations. I don't think it's needed for this course. Okay, but most important one I want to highlight is that the compliance, alright, is denoted by S, and this sigma is just this one. Alright, it's just all of this. While the normal stiffness matrix is C. Alright, so be careful of this thing. Then the next thing you need to know is how to find your Poisson ratio and your Young modulus and your shear modulus. Alright, and this is gonna head back to the definitions that we have just discussed. Alright, for an isotropic, alright, this is for isotropic. These are all your shear modulus and your bulk modulus if needed. Alright, and for isotropic, this is the strain equations, and this is how you put it in the matrix over there lah. But at least you get to know everything already in this section. And I think this is it for the isotropic material, because I don't want to confuse you with another form of a thin plate. Alright, so there is a thin plate subjected to stress condition where it is also an isotropic laminate. Alright, so therefore over here, this is the part that in this video we have talked about it. Alright, so in the next video we'll kind of talk about it for a thin plate, alright, for a laminate. Alright, then we will get to see about it. And therefore, yeah, see you in the next video for this then.